Howdy, welcome to Math 153, Elementary Statistics. I am Lance Curtis. This is the lecture for section 10.6. As you can see, is the last section in chapter 10. And chapter 10 is the last chapter we're going to look at in this course. So what we're about to embark on is the last lecture. Let's dive in. Key concept for nonlinear regression. Well, first of all, we need to understand that not everything in the real world can be modeled with a straight line. So up until this point, we've been using linear regression techniques to model data sets. Well, not everything in the real world is modeled with a straight line. So this means we need to find methods for developing non-linear functions that better fit sample data in certain situations. So, as I said before, we've dealt before with linear relationships. Now we're going to get just a very brief introduction into regression involving nonlinear relationships. We're not going to get into any of the old school methods for making these types of models. That type of math is, in many respects, well beyond the scope of this course. And so we're just going to focus on using software for finding and making our statistical models. The author of your textbook provides 3 basic rules for identifying a good statistical model. So let's go over them. The first rule is to look for a pattern in the graph. So you basically make a scatter plot and you're looking at the plotted points to see, is there any sort of pattern here that resembles the same patterns that we see in basic generic models. Next, we find and compare values for R squared. So, because typically we don't know what type of model we need to make will actually fit our data best, we're going to be making multiple models from different types, and then we're going to be comparing R squared values. So, functions with the larger R squared value have a better fit, and so those are the ones that we're going to favor. And then third, you need to use common sense. Okay, if your model makes a predicted value that's completely unrealistic and ridiculous, then don't use the model. The model's obviously got something wrong with it, and you don't want to be using that type of model to be making predictions. Now, experience that I've gained working in the real world really suggests that, yeah, these are good rules, but we need to make some slight modifications to each one of these when it comes to identifying a good statistical model. So first, yes, you want to compare patterns in the graph with common uses for generic model types. So there are some applications that are fairly consistently modeled with a particular generic model type. For example, radioactive decay is very often modeled with an exponential function because the way half-life works follows the basic pattern of the exponential function. That doesn't mean that your data couldn't be fit better with a different type of model. That just means, hey, if you want to use a different type of model, and it fits the data better, then more power to you. But chances are it's not likely going to happen. So it's going to have to take something truly exceptional for us to model radioactive decay with something other than an exponential model. So to some extent, I don't want to go off looking too far away from the exponential model when I'm trying to model radioactive decay, because the exponential model has been proven by experience to be a really good model for that type of data. Second, my suggestion is to find and compare values for adjusted R squared. Now, you can use R squared values to judge model fit. Okay, there's nothing especially wrong with that. Just understand that the adjusted R squared models are actually preferred. I actually prefer using this value instead of the R squared value because the adjusted R squared value will account for the differences in number of variables. Not all model types have the same number of variables. So you may be looking at 2 different model types. They don't necessarily have the same number of variables, and so the adjusted R squared values will take that into consideration, whereas R squared is just is just looking for model fit and not taking into account sample size or the number of variables that you have. And finally, yeah, you want to use common sense, but you want to pair that with good judgment. Okay? Of course, you don't want to use a model that predicts unrealistic values, but if your model is predicting an unrealistic value, there's something wrong with your model. So you need to go back and try to look at how can we actually make this model so it gives us a more realistic prediction. Usually that means providing more rigor in the data that you're feeding into the model. So is there something that we can do to improve the sampling method? What is the cleanliness, quote unquote, of the data? Okay, is all the data applicable to our specific situation and answering the question that we asked? Go back and look at that. Do we have missing data? Is our data set incomplete? Would we have a substantially better model with just a little bit more data? I mean, these are the types of questions that you need to ask if your model is making unrealistic predictions. And it's well worth your while to go back and try to see what you can do to make a better model. We mentioned generic model types, so this is what we're actually using for comparative purposes when we're trying to figure out how are we modeling a nonlinear data set. So we're of course familiar with the linear model. This is what we've been using up until now. And you can see the general form for the linear model, y equals a plus bx, where a and b are simply numbers that serve as coefficients for our regression equation. But we can also model things with a quadratic function. So you see here ax squared plus bx plus c. In this particular example, the quadratic function is opening up, but you could flip this function upside down so that it's opening down, or you could flip this function on its side so that it's opening to the left or opening to the right, or any of those positions in between those. So if you can imagine rotating that around 360 degrees, any one of those positions would qualify for modeling with the quadratic function. There's also the exponential function, which I mentioned before. So typically what you have with the exponential function is something that starts out small and you see small gains, and then over time you start to see those gains start to pick up and become incrementally greater. And there towards the end, the model just will simply shoot straight up. Power function is simply an exponential function that's a little bit more muted. So notice how it's following sort of the same trend, but it's more flat than the exponential model. So there's your power model. And of course, the logarithm model is the opposite of the exponential. Instead of starting small and building up to where it shoots up, the logarithmic model generally starts shooting up really quickly and then it levels off as time goes on. Here's a table listing some practical applications for each one of these models. You don't need to really know these by heart. I actually have these printed out onto a sheet that you can download off of Blackboard, so feel free to take a look at that. But there are some things, as I was mentioning before, some applications that are typically modeled with certain types of models, and so that's what we see for the most part here in this table. Let's look at a particular example to illustrate. So the table that you see below on the bottom of this slide is listing population of the United States in millions of people for different years. So we're going to actually work this problem two ways. First, because some of your homework problems talk about using coded years for making models, we're going to work this problem using coded years. So you see there in the table coded years. So 1800 is coded as 1, 1820 is coded as 2, 1840 is coded as 3. So we add one more to our coded year every time we pass 20 years in reality. What we're asked to do is find a mathematical model for the population size and then predict how much the population will be in 2020. So the first step is make a scatter plot of the data. So when we do that, here's what we end up seeing. Now what we're going to do is take this general pattern that we see in the data and we're going to compare it to individual model types. This is actually the first of two approaches that we could take for our next step. Okay, so in theory what we should be doing is comparing the pattern of this data set with the general shape of generic model types. And when we do that, looking back at the 5 that we looked at previously, we're going to come up with 3 possibilities. This could be a quadratic model, it could be an exponential model, and it could be a power model. So, in theory, we'd make each one of these different model types, we'd compare the R-squared values, and then we'd look at the scatter plot, make sure it had good fit, and then we'd use sound judgment to figure, okay, does it make sense that we would use this model for modeling this data? In practice, however, because some types of applications are consistently modeled with the same model type, just look at the table of practical applications that we just looked at earlier and use that table to figure out what model we need to make. So if we use that table, general population growth appears as an example of a quadratic model. So I'll end up making a quadratic model. Now, if you want, you can use a theoretical approach. You can make multiple models, you can compare them, and then come out with the quadratic on top when you do your comparison. But if we know the quadratic's going to come out on top beforehand, why go through the comparison? It's much more practical if we just know the one model we need to make, and then we can just go about our business of making and using that model. So we're going to use software to make our model. As I mentioned before, we're not going to get into any of the old school techniques for performing nonlinear regression. So when we dump this data into StatCrunch and use it to make our model, here's the results window that comes out. Notice the regression equation appears at the top of the screen. So here we have the coefficients in the parameters table match the ones that you see up there at the top. So if you want to use those to figure out your numbers, feel free. Either way, the regression equation comes out to be what you see here on the screen. So now that we have our model, we're ready to make a prediction. So we want to make a prediction for the year 2020. Now, do not put in 2020 into this model to make your prediction. You're using a coded year to make the model. That means you have to supply a coded year in order to use the model. The model is based on the data used to create it. So you have to format your data the same way that the data was made to use the model. So because we made the model with coded data, we have to have coded data in order to use the model for predictive purposes. So we can't put in 2020. We have to translate that to a coded year, okay? Which we do. We find that that code is 12. So 12 is the number we're going to punch in to our actual regression equation. When we do that, we get out 336.4121. So a little over 336 million is the predicted population of the United States in 2020, according to this model. Note that in the bottom of our results window, there on the right, we get the same predicted value from the software. So if you input the right predictor value, you can get the same prediction value out from the software. Now, some of you may be wondering, 12 was actually outside the range of data that we used to make our model. How is it that we're using 12 to make the prediction? Well, 12 is outside the range of data, but it's just outside the range. What you want to avoid with extrapolation is getting far away from the range of data values that were used to make the model. If you're just outside the range, and 12 is just larger than 10, which is the maximum value from our data set, then yeah, you're probably okay. You still want to take that with a grain of salt, because who knows what the function's going to be doing, but Most functions that we see in the real world don't have radicals just with them all at a point. Okay, there's usually some sort of transition between different slopes of the line. So if you're just outside the range of values that was used to create the model, you should be okay for making a prediction. We can make our model more user-friendly, though, if we skip the coded year thing altogether and just use the original year data that was provided to us from the get-go. So here's the results window that we saw previously using the coded data for the years. If we make another model using just the original year data without any coding, this is the results that we get. And you can see, looking at the regression equations at the top, that we have very different models. They're both second-order polynomials, so we have quadratic models in each case, but the coefficients are really different. So notice how the coefficients change between the different models. Compare the parameter results in each of the parameter estimates tables. The parameters are very different, but look down below. We see we make the same prediction for population size in the year 2020. The difference with using the original data is that someone using this model doesn't have to translate their year into a coded year in order to use the model. So in many respects, this model that we just made with the original year data is a better model because it's more user-friendly. You don't need to translate your input in order to use the model. Now, when it comes to your homework problems and your assignments, if your problem statement says it talks about using coded data, you need to use coded data because very often you're going to be asked for the coefficients in a regression equation. And as you can see from this example, your coefficients are very different if you don't use the coded years. So if you have a homework problem or something like that that talks about using coded years, I'm sorry, it's a pain, but you're going to have to use the coded years in order to get the right coefficients out for your regression equation. This brings us to some of the limitations that we find in StatCrunch. So whoever it was that built this program, they made some assumptions when they were designing the different features that StatCrunch would offer. And those assumptions guided what was built into the actual product. The first assumption that we see that was made is that they're assuming that you want only one model when performing any type of regression on a data set. So there are statistical software programs that are used professionally, and many of these programs have automated comparison features. So you set this thing going, and it will take your data set and make multiple model types from that data set. And then it will compare them. It will rank them automatically for you and make a recommendation that says this model type comes out on top. It will show you the R-squared values, adjusted R-squared values, p-values, whatever you want. And you can actually then take your judgment and say, am I going to accept what the computer's ranking number one? Or am I going to take one of these other models that, maybe, the second rated or the third rated model, but looking at the differences in the R-squared values, there's not that much difference, and there's some external considerations. So looking at the way that the model fits the data or the predictions that the model make. Maybe the model that's ranked at number 2 makes a more realistic prediction than the model ranked as number 1. So then you can actually pick which model works best for your situation. StatCrunch does not offer any type of automated comparison features because they're assuming you're only going to want one model when you go to make a model. So you have to make the models one at a time. That brings us to the second assumption that was built into the product, which is you know exactly what model you want. Not only do you want only one model, but you know exactly what model that one model is that you want to make. Well, that assumption is fundamentally different than the intention built into the homework problems and the questions you're going to be asked in your assignments, which is they're assuming that you're going to be making multiple model types like we looked at before. They're following the theoretical approach where you make different model types and then you compare those model types and then make your selection based on that comparison. Well, because there's no automated model comparison feature in StatCrunch, you have to make each of these models that you're going to compare one at a time. Oh my gosh, what a pain. But hey, don't fret yet because the party's not yet over. We still have another assumption that's been built into StatCrunch, and that is your needs for nonlinear regression will be few and far between. Now, if you step back and take the perspective of the forest, that's actually a pretty fair assumption. I mean, you look at all the things that we've done in the course of this class, and you see that nonlinear regression is only one section out of all the many, many sections that we've covered in the 10 chapters that we've covered in this textbook for this class. So from that perspective, yeah, needs are few and far between. That's probably a fair assumption. But if you then zoom in and take the perspective of the trees, when you're in that one section, working the homework problems for that one section, working the quiz that's related to that one section, so on and so forth, you're doing nonlinear regression more than just once in a while. You're doing it over and over and over and over again. Well, because they assume that you're not going to need it all that much, instead of building in separate regression functions for each one of these model types, they simply said, well, we're just going to put everything, more or less into, a couple of model types, and then everything that we need, yeah, that's going to come out that way. So we'll just rely on you using some data transformation techniques. And then if you need to use the nonlinear regression once in a while, you can put up with the inconvenience of having to do data transformation. Well, geez, if you're in this one section, you're doing it more than just once in a while. So you've got all this data transformation that you've got to do in order to get the right results to answer the questions. This seems like a whole lot of nightmare. Isn't there a simpler way that we can handle nonlinear regression while using StatCrunch? And we want to use StatCrunch because, let's face it, if we go out and get one of these, software programs that actually does all the things that we really need it to do to make life really simple and easy, we're going to be shelling out some big bucks. So how can we use the tool we already have in a simpler way to do what needs to be done with nonlinear regression? Well, we can't change the assumptions that have been built into the software. However, that means we have to change our approach in order to conform with those assumptions. So how do we do that? Well, first of all, if we could read the problem statement and know exactly the one model that we need to make, we can handle those first two assumptions pretty well. Okay? So you could, again, go through the theoretical approach of making each model individually, but what are we really going to learn from that? I don't know. I mean, if you're actually training to be a statistician, or you're training to be, a quality control professional, or someone who trains people in Six Sigma techniques, or you're looking to be a reliability engineer, someone who would use this sort of thing on a daily basis as part of their job description, then yeah, I can see some value in taking that theoretical approach and making each model individually, then doing the comparison and coming out with the one on top. But the real intention of this course, for most of you, is not to prepare you for one of those careers, but rather to give you familiarity with statistics so that that familiarity can then inform you as part of your preparation for the career that you're really going to have. So what needful principle are we going to learn from making the individual model comparison? I'm struggling to see that. So let's handle those first two assumptions built into the software by using that table of practical examples that I showed earlier to identify your model. I actually went through your homework problems and looked at the model types for each one and used that information to inform that table. Okay, again, You don't need to go back and copy it. I have it up on Blackboard. You can download it. It's a sheet on Blackboard in PDF format, so it's printer friendly. You can just come out, print the sheet, use it for your homework, for your quiz. I will provide it for you for your test, so you don't need to bring it with you for your test. I will provide that for you, but you can use this table of practical examples. Then you'll know the one model you need to make. Okay? Then once you know the one model you need to make, we still have that third assumption to handle. Okay? We need a simplified way of using the nonlinear capabilities that can make that one model that we need to make without a lot of excess complication and fluff. Okay, so that's where we're going to get into knowing exactly what options to select in StatCrunch, and then knowing exactly what to do with the results that StatCrunch gives us. And the simplest way that I know to get that done is to use another table that guides us through each next step of the process. So here's what I'm calling the data transformations table. This is what's going to guide us through the nonlinear regression for each of the problems in our homework, quiz, and the test. Again, this table, you don't need to copy it down. I'm putting it together on the same sheet with the example application table that I mentioned earlier. So all of that's on the same sheet. You can just download that from Blackboard and use it to your heart's content. This actually lets you know which function, which nonlinear model type you need to be making, and it also tells you what options to select in StatCrunch and how to interpret the results so that you can get the answers you're looking for. Notice that we have each of the 5 model types there. So they're on the left. We have the linear, quadratic, exponential, logarithmic, and power models that we were looking at earlier. The next column lists the general form for each of these models. And then we have the regression option that we need to select in StatCrunch in order to make each one of these models. Notice that for the most part, we're going to be using the simple linear option that we've already been using. The polynomial option will be used if we're making a quadratic model. That's the exception to this rule, but otherwise, we're going to be using the simple linear function to make our models. Then we have the options window that comes up. Once we've selected the right menu option, we get that options window that comes up. So this column is going to guide us to know what are the specific options we need to take to transform our data so that it comes out correctly. Then when we press compute and get the results window, the last column here in our data transformation table is going to tell us what we need to do with those results in order to get the coefficients that we need for our general model form. Then that's what we're going to put in to answer our particular homework quiz test questions with. So notice that for some of these data transformations, you see the ln symbol, and that's just mathematical shorthand for natural logarithm. So natural logarithm is a logarithm with the base of e, 2.717, I think it is, and the decimal just keeps going out forever and ever. But that's the natural logarithm base. Hopefully you've had some algebra where you can remember some of this stuff. If you haven't, then it's just a matter of learning what buttons you need to press on your calculator to get this done. But that's a natural logarithm, and that's what we're going to use for actually making our data transformations. So as we saw in the table, okay, if you're looking at a linear, quadratic, or a logarithmic model, there was nothing you needed to do with the results that come out. Just take the coefficients as they appear in the parameters table of your results window and you're off and running. But there's some transformation that's needed if you're looking for an exponential model or a power model. So let's look at what it is that we need to do to transform our data. Let's start by looking at the exponential model. So here we have the general form for the exponential model, y equals ab to the x power. If I take the natural log of both sides, then I can use the properties of logarithms to separate out the a, the b, and the x. Okay, first I can separate out the natural log of a times b to the x, as the natural log of a plus the natural log of b to the x. This is a property of logarithms. When I have a product of two numbers multiplied together, it's the same as summing the logarithms of each one of those numbers separately. Then if I'm taking the logarithm of a number raised to a power, I can just take that exponent and put it out in front of my logarithm. That gives me the same answer. That's another property of logarithms. So now here I have my exponential equation written in a different form. The reason why I want to write it in a different form is because I want to compare this with the general form for the linear regression model. Why do I want to compare with the linear regression model? Because that's the option that we're using in StatCrunch to make our nonlinear model. So in order to know what to do with the coefficients, I need to be able to compare the exponential function with the linear function, and then through that comparison, I can know what to do. So notice what we have with our exponential function. We have the natural log of y equals the natural log of a. A is just a number, so the natural log of a is just going to be some number. And then I'm adding that to x plus the natural log of b. Well, again, b is some number, so the natural log of b is some other number. So I've got on the right side of my equation some number plus x multiplied by some number. Now, compare that with the form for the general linear regression equation. I've got y hat equals b naught, which is some number, so y-intercept, plus b1, some other number, it's a slope, multiplied by x. So I have some number plus x multiplied by some number. So because the form is different, I can look at this and say, okay, I'm going to take the elements that are similar between these two forms, and I'm going to set them equal to each other. So if we look, for example, that the natural log of a is then comparable with b naught in our linear regression equation. So I can go and I can set those two equal to each other. B naught is my y-intercept. So that's going to be the intercept value located in the parameters table of my results window when I go to do the regression analysis. If I then raise both sides, take e and raise e to both sides of my equation, okay, I come this out. And the reason why I want to do that is because then that natural logarithm can go away and I can get a all by itself. And that's what I want. I want to get the coefficient for my exponential equation. So I can get the first coefficient by just taking e and raising it to the power of whatever that intercept value is. Likewise, I can do the same thing for the other coefficient in my exponential equation. So if you look, you can see that b1 is similar to the natural log of b. They're both a number that's being multiplied with the x value in our equation. So I could go and set up the same way as I did before. b1 is equal to the natural log of b. b1 is the slope value from the parameters table in my results window, so I can go ahead and substitute that in. And then, again, taking e and raising it to the power of both sides of my equation, I can get rid of that natural log, and I get e raised to the power of the slope is equal to b. So if I use the table, it makes this easy, because the table just gives me that end result that I need to transform the results I get into the results I need. So I'm just going to take the intercept value in that parameters table, and I'm going to take e to that power, and that's going to give me the first coefficient for my exponential equation. And then I'm going to do the same thing with the slope parameter, and I'm going to get the coefficient b for my exponential equation. I do the same thing with the power function. Okay, so again, starting with the general form, take the logarithm of both sides, and then I can separate out the logarithm there on the right using the properties of logarithms, and I come out with a form, again, similar to the general linear regression equation. I go ahead and make my comparisons. So again, b naught is similar to the natural log of a, so I set those two equal to each other, and then go through the same process that we did before, and we come out with the same solution, that a is equal to e raised to the power of the intercept. But notice that when I go to do B1, okay, the comparable value in the power equation with B1 is simply B. You notice my x is inside the logarithm, and that's okay. There's nothing wrong with that. But what's being multiplied by that quote-unquote x value? Well, it's just a number out in front, B. So when I set those two equal, I've got a number equal to a number. So I can take the slope value out of my parameters table and use it directly as the coefficient. I don't need to make any further transformation to that value. I can use it directly because it is the coefficient that I need for B. So again, it's listed there in the table for the power function. You just take that intercept value and use that as the exponent on the natural log base, and that gives me my first coefficient. And then to get the exponent, which is the second coefficient, I just take that slope value directly from the table, and voila, I'm in business. Let's look at an example to illustrate how these two tables are used in unison to simplify the process for using nonlinear regression inside StatCrunch. So here we have an example involving bacteria growth. In a carefully controlled experiment, bacteria are allowed to grow for a week. The number of bacteria recorded at the end of each day is shown in the table below. So then we're asked three questions. First, what does a scatter plot of the data look like? 2, what mathematical model best fits the given data? And 3, how many bacteria can we expect to see on day 8 at the 5% significance level? Well, first, what we're going to do is look at the model table to determine what model we're going to make. Okay, so when we look at this table of example applications, we're going to go through that list there in the column on the right, and we're going to find the example application that matches the problem we're working with. So if you go through this list, you see bacteria growth is located here towards the center. And what model does that correspond with? Well, that corresponds with the exponential model. That's the model we're going to make. So we don't need to worry about making any of the other four. We're going to go straight for the exponential model. Next, we need to prepare to make our model. So we know what model we're going to make. So let's make some preparations to make that model. So first, we're going to put the data in StatCrunch. Then we're going to Stat, Regression, Simple Linear. Why am I going to Simple Linear? Well, because that's what my data transformation table tells me to do. Here's an excerpt from the data transformation table listing the row for exponential model making. Notice that here in the middle, StatCrunch regression option says use Simple Linear. So that's what we're going to pick to make our model with. Then when we get into our options window, okay, we're going to select the data columns, tell StatCrunch where our data is. So we do that there at the top. And then we're going to go down towards the bottom. There's a section labeled Transformation. So this is where the data transformation table is going to tell us what options we need to select. So notice here in the data transformation table, it says in options window, X is none and Y is ln Y. So now go back to the options window and notice that for the X field, I have selected none. And for the Y field, I have selected natural logarithm ln Y. So now I know what options I need to select. I just select those options and I'm good to go. There's one more thing I need to do, however, and there's this little checkbox down there below the X and Y fields in the transformation section. Make sure that you check that box that says use original units and graph. We're going to look in a moment as to why you need to check that box, but you want to make sure that that box is checked. Then you press compute, go to the second page of your results to see your scatter plot, and you're going to see that the regression line should appear to fit the data. But what you see is going to be different depending upon whether or not you have that little box checked or not. So whatever data you provide to StatCrunch, it's going to display a scatter plot of it. But the pattern that the data points make is going to be different depending upon whether or not you check that box. So if we check the box like we're supposed to, here's what we get for our bacteria growth data set. And this is what we want to see. Notice our regression line follows the general form of an exponential function where we start out small and then we start getting bigger and bigger and bigger. And finally, we're just starting to shoot way up. So we get monumental gains with very little advances in our horizontal axis value. If you don't check the box, here's what you end up seeing. You'll see everything fitted to a straight line. Okay. Now, notice that in both cases, you can assess model fit either way. In both cases, the regression line that you see in red fits the data points that you see in blue fairly well. So you can adjust model fit either way you go. The advantage you get with checking the box, okay, is that if you don't check the box, then the true pattern of the data points gets obscured because it's fitting everything to a linear regression. And that's because you're using the simple linear regression option to make your model. So if you don't check that box, then StatCrunch is going to assume you want a straight line for your scatter plot. Well, what we want to see is the true pattern of the data points, and that's why you check that box. So make sure you check that box so that then you can select the right answer option when you're asked, what does a scatter plot look like? Now, to get to the second question of making the actual model, okay, we've done all this prep work. Now we're ready to make our model. So we go back to our results page, and this is what we see. Notice that the parameters for the regression equation are listed in the format of a linear regression equation, b0 plus b1x. What we want is an exponential regression equation, because remember, we're trying to make an exponential model. So we want the exponential regression equation, and that has a different general form, a times b to the x power. Well, go back to your data transformations table and look at that last column where it says in results window. This tells us what to do with our results so that we can get the coefficients that we need. Just follow those instructions and everything comes out. So the first equation listed in the results window, a equals e to the intercept power. So what I'm going to do, go up to my parameters table in the results window and get that value for intercept. And then I'm going to substitute that into the equation listed in my data transformation table. When I do that, I get a equals e to the 2.6431819 power. And yes, I'm carrying all those digits in with me, so I minimize rounding errors mid-calculation. Come out to be 14.06 when I punch that out on my calculator. Now, the second equation listed in the results window for b equals e to the slope. So what I'm going to do is, again, look at the slope value there in the parameters table, and I'm going to substitute that in for slope in my equation. So b equals e to the 0.637232227. That punches out on the calculator to be about 1.89. So then I go back to the general form for my exponential function. Okay, y equals a to the bx, and I'm going to substitute in the value for a and the value for b. And that comes out to be what you see here on the bottom of the screen, 14.06 and 1.89. So then my regression equation is y equals 14.06 times 1.89 raised to the x power. Notice the regression equation is not the intercept and slope values taken directly from the table. It's not 2.64 times 0.64 raised to the x power, nor is it the linear regression model that you see up at the top of the results window, 2.64 plus 0.64x. The regression equation follows the form of the exponential function, and those values for the exponential function are the transformed values in the linear regression results analysis. So you can't just take the results from the results table if there's an equation listed there for that coefficient in your data transformation table. Now, if it says that a equals intercept, for example, then just take the value out. If b equals slope, then just take the value out and use it. There's no transformation needed. But if it says e raised to some power, then yeah, you're going to have to get out your calculator and punch it out. A little bit of a pain, yes, but again, not too far different, as simplified as it can be, and not too far afield from what we did previously. Remember when we were looking at confidence intervals back in Chapter 7, and we did confidence intervals on standard deviation. Well, StatCrunch has no direct way of making that, so we had to use the roundabout technique of making the confidence interval for variance and then taking the square root from the results table. This is a little bit similar. This is somewhat similar to that. So again, it's more work than what we really want to do, but it's as simple as we can make this. So this is the way we're going to approach it. Once we have our model made, then we can easily make predictions. Okay, go back to the options window, and there in the prediction area, go ahead and put in your predictor variable and the appropriate confidence level. Now, keep in mind that you've got to put in the predictor value with the same format as the X values used to make the model. So, if your X values are coded years, then you have to put in a coded year to make a prediction. If your model are, say, in units of 100 or 1,000, then you have to use those same units when you make the prediction so that your prediction will come out okay. Because, again, the model is only as useful as the data used to make it. And so the format of the data governs how the model gets to be used in the end. We were asked to make a prediction for day 8, and we were told that alpha was at 5%, so that means we have a prediction level of 95%. So I put those values in and then press compute, and then I just read the predicted value right off the results window. So here down below I can see there's going to be about 2,300 bacteria at the end of day 8. Again, if we want to make a prediction interval instead of a predicted value, we can just read that right off the table as well. It's there on the end. And that brings us to the end of this last lecture. So if you have any questions, you know what to do. Otherwise, I will see you in class for our last lecture, class activity time. So I will see you then. Thanks for watching.